In this chapter, we're going to talk about risk management, which involves two main topics, which are duration and convexity. The chapter is divided in 6 modules. The first module will talk about duration, which is the first derivative of bond prices to interest rates, also called delta. Then we're going to see how to do something called immunization with delta. That's how to manage portfolio interest rate risk. Then we're going to see the definition for convexity, and in particular, we're going to see a new definition called gamma, that's the second derivative. The fourth module is going to be on managing interest rate risk, and there we're going to immunize with gamma, and here also delta. Then we're going to see the definition of theta, which is the sensitivity of bond price to the change in time. And finally, we're going to define barbers and bullets. First, we have to realize that bonds are sensitive to interest rate changes. So here we have the interest rate, and then you see that as the interest rate goes up, the bond price goes down. So that by itself is some kind of risk that we're going to have to manage and understand. Part of the motivation goes like this. If you have some interest rate R and you have the price of your bond, and now let's imagine that interest rates go up, then the bond price goes down, and you have your change in price. So what you could do is just go compute this price, compute the new price, and then compute the difference. One of the things we're going to do in this chapter is that we're going to compute the derivative, the sensitivity of this bond price to changes in interest rate by using duration and convexity delta gamma. And you can imagine that it's going to be like the delta, the first derivative is going to be this line. And then this is also going to allow us to get a new price change. So in this case, the price change would be bigger, but it's going to allow us to compute this change in price in a different way. Why do we want to do that? Well, when you have one bond, it's easy, but for banks, that's not the case. Banks can have in their portfolios hundreds, even thousands of bonds. And when you have thousands of bonds to compute the change in price for all those bonds to be able to manage risk, it's very, very hard. So, and to do this delta gamma approximation or the duration convexity, it's much easier. Let's start with something that you should already know, which is the yield duration. So the yield duration, also called Macaulay duration, is defined as follows. So these are basically the cash flows that are going to be paid from 1 to t, discounted at present value. So each one, this part here is the first cash flow discounted, second cash flow discounted, and so on. You multiply here by time, and then you divide by the bond price. And then this y is the yield to maturity of the bond. Some people think of the Macaulay duration as a weighted average of the cash flow times. So sometimes you're going to get a number that it's going to be, let's say 7, and people say, well, I'm going to receive my cash flows on average in year 7. Some are going to be before, others after, but on average, I'm going to receive all my cash flows in year 7. In particular, the Macaulay duration of a zero coupon bond is equal to its maturity. So I receive everything the last day. Hence, it makes tons of sense that the Macaulay duration in this case is the maturity. Another definition that you should already know is the modified yield duration, which is a function of the Macaulay duration divided by 1 plus the yield. What do they mean? The Macaulay duration is also equal to the change in price divided by the price. So here we go back to what we're going to be doing in all this chapter, which is a change in the price of the bond. The Macaulay duration is equal to the modified duration by multiplying it by the change in yield. Hence, you can include the change in yield to be able to understand how the price is going to change. Now, one of the problems that you have is that the same problem that you had before, with yield to maturity. That yield to maturity works really well if I only have one bond. So here, same story. Macaulay duration or modified duration, they work really well if I only have one bond in my portfolio. So if you have yield to maturities for different bonds, those are going to change differently when the term structure is not flat. Remember that the term structure is the zero coupon curve. And this is even when there are parallel shifts. Parallel shifts is that all the zero coupon curve goes up, let's say, by 10 basis points. Another problem is that we cannot combine the yield durations of bonds to find the portfolio duration. So let's say here you have yield duration, so dy, for bond 1, and then you have another one for bond 2. So then you have your portfolio. So the question is whether the duration of your portfolio is equal to the yield duration of bond 1 and the yield duration for bond 2. The answer is no, it's not equal. So that's going to present a real problem when you're trying to do risk management, because these yield durations are not additive. So if you want to do portfolio risk management using yield duration, you're not going to be able to do it properly. So what are we going to do about that? We're going to see a new way of measuring the sensitivities of bond prices to interest rates, and we're going to use calculus. In specific, we're going to use derivatives. So what's the logic behind that? The logic is by using something called Taylor series expansion. Taylor series expansion tells you that if you have, so this part would be what so far we call the change in price. And we're saying, look, the change in price is equal to, this would be the first derivative, and then we're going to see first derivative of what? And then here it's going to be times the change in rates. So this first derivative is the first derivative of the bond price with respect to rates. So how is this helpful? Well, once you have your first derivative and you want to find out what the change in price is going to be for a given change in interest rates, you can do it directly. So you have your first derivative, and then you say, oh, imagine that Mexican government is going to lower the interest rates by 25 basis points. Then you say, look, then my portfolio, you're going to multiply that first derivative times this minus 25 basis points, and then you're going to get what the change in price is going to be for your portfolio. Now here we're going to compute the sensitivity of zero prices to the interest rate. So our definition of the bond price is as follows. So we're going to take this one. So for short, this is going to be B equals K E to the minus RT. And then you have to take the derivative of B with respect to R from here. It's going to be K. Then the derivative of e to the minus RT is going to be times minus T. And then again, we are left with e to the minus RT. And then we see that if we take these two things together, that's exactly the same bond price. K e to the minus RT, the bond price. And then we're left with minus T times the bond price. So our Taylor series approximation will tell us that the change in the price of the bond is going to be approximated with minus T times B, and then here the change in the interest rate. This is the first important definition of this chapter, and one that we're going to be using for the rest of this course. So it's the dollar duration. So dollar duration, we're going to write it as delta dollar. So I'm going to call it either dollar duration, or I'm going to call it delta for short. And it's going to be equal to minus the change in price for a 1% point change in interest rates. So here I have the definition of delta dollar. Delta dollar is going to be equal to T times B over 100. So basically I took my derivative from before, minus TB, I put a minus sign in front, and then I divided by 100. So now the change in price is going to be equal to minus the delta dollar times the change in interest rate. One important thing is this derivative was taken using continuously compounded rates. So then every time we work with this formula, you need to use continuously compounded interest rates. That's one thing. The other thing is all this explanation here of 1 percentage point means that if interest rate change from, let's say, 5% to 6%, then here you have to input 6 minus 5 equals to 1. You would put actually 1. That's what it means. And another way of understanding it is that's why we're dividing here by 100. We're going to see how to compute the delta dollar for a coupon bond. So a coupon bond is basically a sum of 0 coupon bonds. So hence, the change in price is going to be very, very easy to compute. We're just going to take the sum of the changes in 0 prices. So basically, the delta dollar of a coupon bond is going to be the sum of individual deltas. So in this case, for a bond with maturity T, you're going to have to take each one of the PVs of the cash flows and multiply it by the time when it's going to be paid. And then at the end, you're going to divide by 100. Now, one of the things that you need to clearly see here is that contrary to the yield to maturity, here we have RT. This means that R1 is different from R2, which is different from R3, and so on. It also means that here we have what is called zero coupon yield curve or term structure of interest rates. But this is important because we're departing here from the notion of the yield to maturity. Now, what's going to happen when there's a parallel shift in the term structure? We're going to be able to approximate our changing price. And one of the important things is that the delta does not assume that the term structure is flat. So this means that your term structure, here you have your R and here T, so the term structure does not have to be flat. It can be increasing, it can be decreasing, it doesn't matter. So the assumption is that our approximation is really, really good if the term structure makes parallel shift.
An alternative sensitivity that is mainly used at banks is the DV01 or the PV01. The DV01 is basically defined as minus delta dollar over 100. And it basically measures how much is your portfolio going to move by 1 basis point movement. So imagine that the PV01 is $50,000. Then 1 basis point movement is going to make your portfolio change by $50,000. So imagine the Fed says, okay, I'm going to cut interest rates by 25 basis points. Then your portfolio is going to change by 50,000 times minus 25. So it's 1.25 million.
Now let's see an example of a delta calculation. So here we have 3-year bond. It pays any annual coupons. The coupon yield is 14% and the face value is 1,000. Now, because this thing pays coupons twice a year and it's a 3-year bond, then in total we're going to have 1 to 6 coupons. Coupons are going to be $70, all of them. And then the last one is going to include also the face value. These are the cash flows, 70 all the way and then 1070. And the discount factors are given, so I give them to you. And then the question is, how do we compute delta? So delta, as we saw before, is basically going to be times PV over 100. So here I'm just going to do first the T times PV. So I do it for all of them. Note that here T is going to be equal to 0.5. So this is going to be T times PV and so on. So at the end I end up with this number for all my bond. Now I know that the delta dollar is that number divided by 100. And that's how I end up with delta dollar of 28.1594. Also, the value of the bond for your reference is 1094. So what does this mean? This means that the change in bond for 100 basis point movements in interest rates is minus $28.15. Now, in the second example, so I want you to read the problem, and then I want you to go and do it yourself. So here we're going to do small changes versus large changes in interest rates. So we're going to consider a 20-year bond with annual coupons of 10% and it has a face value $100. Now the term structure in this case, it's flat, okay? And is at 10% with annual compounding. Or it's 9.53 with continuous compounding. Now it's important to know that the rates that are going to change, because we're going to use delta dollar, are going to be the continuously compounded interest rate. So it's going to change from 9.53 to 9.54. That's 1 basis point. And then the other change is going to be 200 basis points, so from 9.53 to 11.53. And then what we want to do is we want to compare what the actual price change was versus the delta based approximation. And then this is going to allow us to conclude when is the approximation good. Let's look at the example. We're going to compare small versus large changes in interest rates. The delta of a bond is going to be 9.3663. That's what you should go and compute in Excel. And this is per 100 basis points. Now, if I shift interest rates by 1 basis point, that's going to move from 9.53% to 9.54%. So then let's go and compute the real price change. So the real price change is using the pricing formula for the bond. The real new price is going to be 99.92, and the real price change, this is what actually happens in real life, is 99.92 minus the original price, which we know was 100. So basically this thing dropped by 8 cents. Now if we go and use our delta to compute the delta dollar price change, so the delta dollar price change is going to be minus delta dollar times 1 basis point, which is written as 0.01, So this is equal to minus 0.094. So basically, there is about 1.4 cent difference. So this is actually minus 8 cents in reality versus minus 9.4 cents in the approximation. Now let's see what happens when there's a change of 200 basis points. In this case, the delta dollar is going to be equal still, same thing, 9.3663. Now, when rates move from 9.53 to 11.53%, then the real keys prices are going to be, so here we know it's already 100, and here the new price is going to be 83.64. That means that the difference is going to be here 200 basis points for the rates, and then for the prices it's going to be minus 16.36. That's how much my bond price decreased. Now, the delta dollar approximation tells me that it's going to be minus delta dollar times 2, since this rate's changed by 11.53 minus 9.53. That's the change in rates. And this is going to be equal to minus 9.3663 times 2 equals minus 18.73. So you can see that when you compare these two numbers, the approximation when there's big changes in interest rates of 200 basis points is not that good. Not good approximation.